Terry Dennery, the Math Works. So here we are in, I think this could be video 11, and I think that's where we kind of justify the title of the series, Start with Mechanics, because it took us to video 11 before we even began to talk about electric motors, right? And this is a permanent magnet synchronous motor. It's controlled with field-oriented control, and I have videos I've done a couple of years ago that really kind of get into this topic quite heavily. But anyways, we got here, and I'd say the key point here is right here. Look at this. The key input, everything else is basically feedback. The key input for field-oriented control is the torque. As soon as I learned that, I was like, this is remarkable. You know, the electrical and the mechanical guys are really not that different. They're thinking the same things. So anyways, let's kind of proceed up here. I'll kind of show you, this is the simulation we did. The mechanics for the current demo is about as simple as it gets. It's driving the rotation of a constant inertia. It means that, if you divide that electromagnetic torque by inertia, well, that will give you the rotational acceleration you just integrated twice to get position and velocity. And through all this, we figure out what the voltages will be. This is a little bit of a rehash that I've gone through in other videos before, but you kind of get to these constant rotational velocities, and then you see the three sine waves for the three voltages, and they're perfectly, whatever I'd say, balanced. And again, our mechanics is as easy as it can be. There's not even friction. Therefore, all of the torque takes place in the acceleration phase, right? And that's what we're seeing here for current. Of course, current and torque are very correlated. So anyways, without further ado, let's use this. So let's get back to, right there, the model from video 10. We just made everything discrete, and here's where I want to get. We've been kind of working with this idea of, well, because electric motors work so well, we're highly confident that we can deliver the torque that the controller has come up with to make the robot move the way we want it to do. And so we're really going to finally do that now. And so, will that motor I was just showing work? It may not. I'd be a little bit careful about it. I think there's also all kinds of reasons why you would choose another motor. Could just be packaging. You want something flat and small. And certainly affordability will always come in. But again, motors are kind of cool because they can deliver for all kinds of applications. But in general, it's about torque and speed. And so I'd say that again, coming back to the theme of mechanics force, well, we got that because we did mechanics first. So here's what I'm going to do. I'm going to put in a scope, and I want to put in a motor for the FA. That's forearm. So I know what its torque is, and then I want to know its velocity. And that's kind of buried a little bit into the bus signal there. So let's get a bus selector. Forearm. Double click on this. Oops. And we will choose motion. Okay, and then we gotta get one of these selectors because we want to get the velocity, and the velocity will be the second signal. P, V, A. So we want V. Even though rotational, we call it W or omega or whatever. All right, so anyways, let's run our model where we're measuring torque and speed for the robot. Hit run, go to the view. Layout. So we got torque up at the top and we got speed here. All right, and so it looks to me that absolute value is what I'm most interested in on torque because I don't really care too much about directionality. Could have some issues that will come back in tune later on. I'm seeing a little bit of oscillation on speed right there, but let's not worry about that. That's not our point for this demo. Uh, so it looks like probably about zero point 0.4 Newton meters, and then velocity looks like about 5 radians per second, right? And so here's what we want to do. We want to copy this, and we want to copy this too, because this is what allows the electric circuit simulation to be simulated. So it's called the power GUI. All right, and we want to put that in here. Let's see, all right, so the basic idea is the torque command feeds into that, and then the torque delivered goes in there, right? And for this to work, we need some feedback, and so one of those will be velocity, and the other one will be position. So this 1, comma 2. Oops, I think I'll just do this with the demux. So velocity will go like that, and position will go like this. And we'll recall half a Newton meter. So our stall torque of 700 is way too big. I'm going to suggest let's try 1. And for 10 radians, or for 5 radians per second is our top speed. Maybe we'll put in a no load speed of 10. Yeah. Again, these are limit conditions. Stall torques when it's not moving, of course, and no load speeds when it's moving at its fastest. So um, that all looks good. For such a smaller motor, it'll be much smaller inductance, and I'll do that. And I'll go with 1 pole pair for right now. And let's see, let's use this now. Just look at voltage and current. All right, and so I'll hit run. Let's see how we do. Okay, so the 4-arm one is this right here. It's a motor that's driving that axis. So far, so good. It's actually carrying a torque right now. There's a little bit of imbalance with regard to that rotation axis, and that motor does have to carry a torque. Okay, and so we can see that indeed we do need to do a little bit of fine tuning. All right, so that what'll change. And so I'm going to go into controls again, and again, kind of shooting a little bit from the hip here, but I want to tune this PID. Let's stop it. Okay, recall, still at 10, so let's tune this. So there's our PID tuner. It's kind of hard to optimize using just straight standard techniques when it's not SISO, single input, single output. Um, and in general, I think it chooses to go pretty weak, and these are really low values for the gains. And so my general strategy is just kind of make it stronger and stronger and stronger, and you begin to get to a place where it's having a decent response to a step command. And I think that's probably pretty good. What are those values? Yeah, okay. That's it uses a lot of I gain. So that's interesting. So we'll update that. and we will run it again. So that looks much better. Okay, so quite a convenient trick to have in your arsenal, this ability to fine tune your PIDs. Right, and so we used it before and we used it again and got it to work here. All right, and so I think I'll come back to um, here and just tidy things up a little bit. All right, and so what I want to do is I want all that, and of course all of this. I want to put it in a box. Oops, I'm still running. Put in a box we call a subsystem. And I kind of like that. Um, don't really need that second output port. And I could leave it empty, but I generally put terminators on the ports that I don't use. All right, and perhaps just clean this up too and move it. Something like that. Okay. All right, and so that gives me the ability to do it again. Um, again, what we got here. Might want to bring these parameters up to the top. The other thing we do actually is let's put in 4-pole pairs. Because we can see that's kind of the voltage profile with just one. And so put in 4. And I'm going to be a little bit lazy and not do my whole speed and speed and torque analysis, but just kind of assume that these are all pretty close. And so torque command goes in there. This comes in here. And the feedback loop this time is on the wrist. And so I just need to kind of take that like that. And with that, I'll have 2 motors. All right. And so let's hit run one more time. And it seems to work pretty well. So just kind of wrap up on this one. Check out the voltage and current. We don't need to run any further. And with 4-pole pairs, we'll basically see a fair bit more oscillation, right? And so that's on the wrist. Okay, so anyways, idea of this is start with mechanics. Well, we did start, and I think, just observed one of the benefits of starting with mechanics is that once you're ready to put the motors in, the application of a motor, not because it's easy, but because it's consistent and well understood, can be done pretty efficiently. So anyways, thank you.